SwayamPrabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 23. We will discuss today about the various solidification processes and what are the kind of time scales which are involved in such solidification in the molds, and maybe in green sand mold, and then molds used made of metals and metals with cooling. So these three cases we will try to identify to sort of cover the length and breadth of what are the different kind of processes which take place in the casting industry. So let us talk about cooling and solidification. So obviously I think it is needless to illustrate that a clear understanding of the mechanism of solidification and cooling of metals and alloys is very important for production of successful casts, because solidification really determines the grain structure. So as such, the crystal structure and alloy composition are sort of decided through how it is solidified. And typically the mechanism of solidification in pure metals are typically when the liquid metals are cooled below their freezing points before the solidification starts to take place. And why they are cooled is that energy is needed to create surfaces for new crystals. Okay. So therefore you have to have less of kinetic energy so that the such surfaces can start to get created. The degree of supercooling necessary is reduced by the presence of other surfaces or particles which would serve as sort of nucleating sites. So wherever there is a solidification happening, you already have seen earlier how in the polycrystalline materials, because of solidification there are different grains which have grain boundaries, which are separated by grain boundaries, which make the whole polycrystalline materials structure. So if there are certain particles which have higher thermal conductivity, they may be essentially acting as the nucleation sites for development of such degree of supercooling that is necessary for crystal growth processes. And let us say if there is a metal which is at a temperature theta 0 at time t 0, the temperature everywhere is theta 0 within the metal, and the mold phase would act as the nucleus for crystal growth, because that is the coolest phase. So let us say we are talking about the mold phase along this particular line. Okay. So this is the mold phase and this is corresponding to certain distance from the mold phase. So at different time instances, as you can see, there are different temperature gradients which would result, and particularly the mold phase being the one where most growth would start to take place, because it is the cooler point in the whole casting. The fall in temperature would be most at the phase, and then slowly if you look at how the temperature falls down within the mold away from the mold phase, the temperature difference is lower if you go away from the mold phase. Similarly, so obviously the temperature difference is more as with time. So at a certain instance of time t2 greater than t1 from t0, the total amount of temperature difference in the mold phase is more, and this gap grows wider and wider in comparison to if you go more towards the center of the mold away from the mold phase. So mold phase is really the one where maximum heat transfer takes place. And so as the solidification progresses gradually inwards, long columnar crystals like what has been shown here with their axes perpendicular to the mold phase grow. And supposing if the situation was little different, that we had an alloy instead of a pure phase, we can see how there would be a slight variation because of the alloying effect. And let us look at this particular case where there is an alloy of temperature of between two phases A and B, which is 100% A along this particular line and then 100% B along this other end, and there is a liquidus and a solidus temperature where the beyond which the alloy would be completely liquid and below which there would be a solid plus liquid phase, which is present also in this particular zone, and below the solidus line there would be solid phase present. So, that is how you have arrayed this. I think I have illustrated this how this solidus and liquidus needs to be plotted in a lot of cases before in the portion on engineering materials. So, during this process the solids separating out at different temperatures possess varying compositions, because obviously there is also a concept of, or there is also an additional constraint of the solubility of the solid in the liquid phase as a function of temperature. So, the solid phase may not be always 100% soluble, and there may be a certain critical solubility beyond which the one of the phases may not go into the solid phase. Okay, one of the phases may not go into the solid crystal, okay, and in the liquid form their solubility may be different. So, in that kind of a situation, obviously the point where the solidification is taking place, which is also known as the liquid solid front, the composition would be a function of time, because obviously if supposing the solid phase is rejecting a part of the or the solid state is rejecting a part of the phase B, for example, okay, because it cannot contain B beyond a certain percentage. So, immediately in the near vicinity of that solid liquid interface, the composition of B or the percentage of B would get higher because of this throwout of the solid crystal into the liquid. Okay. So, therefore, there are several such compositional changes which are at that solid liquid interface, which may result in a lot of problems. In this particular case, for example, let the liquid alloy have composition C0 of B in A. So, you can see here that at this particular point, for example, composition of B is C0 and that of A is 100 minus C0. So, also let theta f be the freezing point of the pure metal at A. So, this is theta f right here, and theta 0 and theta 0 dash are the respectively the liquidus and the solidus temperatures. So, you can think of at C0 composition, theta 0 is the liquidus temperature and theta dash 0 is the solidus temperature corresponding to this composition C0. So, as the liquid alloy is cooled down to the temperature theta 0, so from here you are basically trying to cool it down to a temperature theta 0, the solid starts to separate out and the concentration of B in the solid is now only reduced to C1. Okay. So, if you want to really make a situation where the further cooling of the liquid alloy is done and it is cooled down to the temperature theta 0, as you can see here, the solid would start to separate out, and because now it cannot hold beyond C1 percentage composition in the solid phase. Okay. So, as a result, the concentration of B in the liquid near the solid liquid interface, as I had just mentioned, increases to a value more than C0, because obviously whatever part has been thrown out of this solid liquid interface, because it cannot get accommodated within the solid, just goes in the near zone, I mean. So, this is the solid formation and this is maybe the liquid, and so if the solid cannot hold anymore the composition of B, that B is precipitated into very near to the solid liquid interface. Okay. So, the percentage here would definitely go above C0. So, it will be somewhat greater than C0, whatever be the percentage composition near in this particular zone, and because of that, if you look at how the percentage of B is varying as a function of distance from the mold, the figure on this left shows this situation where the solidification front has progressed up to some distance d, for example, from the mold phase. So, now let us consider 2 points P and Q within the alloy, within the liquid alloy, and P being just beyond the solid liquid interface. So, it is just the state where solidification has happened as indicated in the figure, and the solidus temperature corresponding to the composition at P and Q are respectively theta dash P and theta dash Q. Okay. So, Q is somewhere in the near vicinity. So, it is actually in the liquid phase. So, you have P as a point and again Q as another point very close to each other. So, you can see that the composition of Q, the composition of this zone P which is near to the solid liquid point, is percentage of B is slightly higher in comparison to that of Q. Okay. So, obviously, they will have different solidus temperatures. Let us just go back to see what. So, the solidus temperature, for example, at a lower concentration is higher in comparison to a higher concentration, the solidus temperature is lower. Okay. So, therefore, the theta dash P and theta dash Q, which are the solidus temperatures at P and Q, are quite variant because of the change in the percentage composition. So, there may be a case where actually the theta P and theta Q are the sort of the actual temperatures as P and Q respectively, and theta Q is obviously more than theta P because the point Q is far away into the mold than P is more closer to the face. Okay. So, if both the theta Q minus theta P, this temperature range, it basically lies within the range of the theta Q dash minus theta P dash. So, there is a case where let us say because of the varied solidus temperatures, now there is a wider range which has been introduced here, because obviously the theta P did not because it is into the solid, it has a lower concentration, and theta Q dash has a higher concentration, because of which the solidus temperature has come down. Okay. So, still there is a case where this theta P minus theta Q actual temperature difference between the point Q and P are lesser in comparison to theta Q dash minus theta P dash. So, this can only be sort of working out if theta Q is lower and then theta Q dash, or theta Q dash is higher than theta Q. Okay. So, very importantly, if such a situation happens when theta Q dash is higher than theta Q, then we can say that the liquid at Q has started to solidify because it is being supercooled. Okay. So, Q is supercooled whereas P is not, because probably the range of P or the theta P is probably higher than theta P dash. That is the only way that this this condition of the range theta Q dash minus theta P dash is greater than theta Q minus theta P. So, whereas the Q is supercooled, the P is not, because P, the actual temperature is higher than the solidus point. So, still it is in the liquid phase, whereas still it is in the sort of it is not yet solidified completely. So, it is in between, and this theta Q dash, because the actual temperature is lower than that, there is a sort of a degree of supercooling which is there in the phase Q. So, what is happening now because of this, that the columnar orientation of the crystal is hampered because of this, and there is a side growth of the crystal at the point Q. So, it effectively turns out that although the preferred growth direction is from the mold phase onwards, but because of the effects of concentrational changes near this area where it is solidifying, let us say this is the solidification front, there is going to be a sidewise growth. Okay. And this is also known as the dendritic growth of the crystal structure. So, the crystal growth in such a situation may appear as on the figure. Dendritic structure is produced if the crystallization at Q gets completed before it starts at P, due to very small thermal gradient within a high concentration difference and a very slopy solidus line. Then randomly oriented crystals would appear inside the casting. Okay. And because of this randomly oriented crystals, you may not have a single directional or unidirectional growth anymore, and the presence of these solid crystals ahead of the solid liquid interface makes life more difficult, because now beyond the point where you are estimating the solid to happen, actually the solid is getting formulated. Okay. So, therefore, feeding the liquid metal becomes more difficult because of such solid liquid interface, and it also implies a greater risk of having voids within the casting, normally referred to as centerline shrinkage. So, one remedy to avoid the aforesaid problem is to produce a large thermal gradient within the mold by providing a chill at the mold's end, so that the gradient is increased so much that this value theta q minus theta p produced by the chill becomes automatically elevated from theta q dash minus theta p dash. So, that once again the normalcy returns and there is a unidirectional growth prominently happening. So, that can only happen when you chill the mold end by putting some kind of a metal insert which would be formulating the rapid heat transfer from that particular point. So, you can create various temperature gradients which are large in nature, so that the Q does not get solidified before P because of the concentrational variation problem. So, if theta P is considerably below Q, then the degree of supercooling is not significant, whereas significantly different at P and Q. A gradual progress of solid liquid interface can be ensured in that case. So, the problem is obviously less critical for alloys having a smaller temperature difference between the liquid and the solid dust line. So, having said that, you have some idea now about how the grain growth would start to happen, or how the crystallization would take place. I would like to sort of end this session here, but in the next session I am going to give you a more fundamental introduction into how to find out or estimate the temperature within the casting given a certain boundary condition based on simple heat transfer theory. Thank you so much.